questions? Okay. Mm-hmm. Yeah.
On your solution,
Mm-hmm.
in the problem, you know, specify which direction you don't have a force.
Do you have it there? I can't even picture what problem this is.
I don't know which one.
Okay. I would consider carrying like one of those throwing stars. If that helps. Oh, I don't need a permit for that. Oh. Well, what's the problem then? Oh, they are? Oh, you do? Okay, that's gonna be a problem. The discs. Oh, yeah. Yeah. Oh, then okay, then that's a problem, I guess. So the pin is here. The weight, yeah, it needs to be acting like this. I guess I just forgot to put that in. That is 20G. Okay, so that's all you wanted for that. This is rigid body kinetics. Okay. No, I don't want that. It's probably wrong. Yep. Okay, so it's rotating about, this is a pin here, I assume.
He's carrying $8. You break it down into two rectangles.
Yep, so this seems like the easiest way to do it. One there and one there. Mm-hmm. Okay, where did I put the coordinate system? At the pin? Okay, so, and we're given that distance from here to here is 0.35. And so we know that the whole thing is 0.6, so we know that from here to here, well, I mean, the whole rectangle one length is 0.6. It's not the middle, right? So this is 0.25, and the thickness, so this is 0.05. And so the x should be 0.25 to get to here, and then another 0.05 to get there. So 0.3 should be the x bar for rectangle 2.
Wouldn't it be 0.05 divided by 2?
Yes.
Okay, so that's the mistake you made.
Oh, I did the same thing there. Yeah, 0.25 plus half of that.
Yeah.
So 0.275.
Okay.
Okay.
Thank you.
Sure. Any other homework questions? Yeah, sorry about that. I was probably watching like Dukes of Hazzard when I made that.
While practicing your
I don't need practice. I don't want to get too. I don't want to get too make it too like. It just looks like this. but then like a star flies out. I assume so. Yeah. Yeah, I'm not sure. Okay, so here is the next example. And we'll think of this as sort of like, you know, you can imagine the biomechanics. Similar calculations would be used for figuring out sort of sports medicine type things. So let's say that, a what? Oh, Bender, the robot? Sure. Yeah, that's a good idea. We will. And we'll say that the lengths are each half a meter. And the mass is, how much do you think one part of your arm weighs? 2 kilograms each? More? Depends on the arm, I guess. Yeah, exactly. Well, let's say 2 kilograms. The numbers that we get out of this, you don't want to base any kind of surgery on. Yeah, I already booked the OR time. We'll call this member 1 at the bottom, and this member 2. And we'll say that at the instant shown, the angular velocity of member 1 and the angular velocity of member 2 are both negative 10 radians per second. Okay, so this is like supposed to be an instant in a throwing motion. Okay, somebody's like throwing the ball, and we're gonna we want to calculate the acceleration of the point up there. I'll call this A, B, and we want the acceleration at C. When an external couple is applied, before I go into that, physically think about what it means to have both of those have the same angular velocity. So there are really 2 ways you could maybe think about this. One is right and one is wrong, though. So do they both have an angular velocity of negative 10 radians per second relative to the ground? Or does this one have an angular velocity of negative 10 radians per second, and this one is rotating negative 10 radians per second relative to the first one that it's riding on? This is important. It's really the ground is what it is. So if these both have an angular velocity at this instant of negative 10, it means this angle of 90 degrees is being maintained and the whole thing is just moving together. Okay. So their orientations are changing relative to the ground at the same rate. Well, it's not rotating relative to the first one. That's right. But you know, their orientations are changing at the same rate. Yes. Yeah, well, so just remember that angular velocity always is in reference to the ground. So this isn't going 10 radians per second relative to this. Somebody resting on member 1, watching member 2, thinks that it's still, because those are both measured relative to the ground. Okay. Always. Yep, that's right.
The 90-degree angle will be maintained. That's the whole problem.
Yeah, well, we're not. Yeah, because we're not. We're just doing an instant. That's right. But Yeah, and we're going to have an acceleration on C anyways, and even if we didn't apply any forces and stuff because they're centripetal accelerations. So let's say that there's an external couple on each of these. So I'll say M1 is positive 100 Newton meters, and M2 is negative 100 Newton meters. It turns out that if you have a muscle that's attached to each of these two body segments, what that muscle force does is apply couples, equal and opposite couples to the two attached joints. And so these are both rotating. Let's do it the other way because we want to. So we want to apply a couple to 2 that's going to, make it straighten, and apply a couple to 1. So basically, we're trying to, M1. Oh yeah, no, that's right. I was thinking the other way around. Okay, so we're trying to apply a couple that's going to tend to straighten the elbow. Okay, so think about that. Does that sort of make sense that that's what this will do? On M1, we're going to apply a clockwise moment. On M2, on body 2, we're going to apply a counterclockwise moment. No, a clockwise moment. And so that's going to straighten that elbow. And we want to calculate the acceleration at C. You think so? No, it's going, no, it's like this. Yeah, in Japan we get that angle all the time. He just broke his elbow. 6. Time to learn curveballs. Okay, so what's the acceleration of C? Okay. All right, so we're going to go through the linkage steps. That means first we do the rigid body analysis of the two members. So first, member 1. Is there a fixed point? Yep. So we're going to go about the point A. The moment of inertia about A is 1/12 times the mass of 2 times the length squared, 0.5 squared. We wanted about A, so we also have to use the parallel axis theorem part. This would be the moment of inertia about the center of mass. So parallel axis theorem part is the mass of 2 times the square of the distance from the center of mass to the about point. So what's the distance from the center of mass to the about point? 0.25. So square that, and can someone tell me what that is? repeating. 0.16 repeating. Okay, now free body diagram. we have a force RA. We have a weight force of 19.62. We have the force on 1 by 2. And then we have the external couple on 1. That's a counterclockwise couple. So 100 Newton meters. And that's everything. Our about point is here. Rho, force, moment. So first that force RA. The rho vector is 0. Force vector is RAX, RAY. Moment is 0. Then the weight force, that's 0.25 times cosine and sine of 45. So that is 1768.1768. Force vector is 0, negative 19.62. What's the cross product? Negative 3.47. And then the force F12, the rho vector is 0.3535. 0.3535. Force vector is F12, X and Y. Bless you. Cross product is 0.3535 F12Y minus 0.3535 F12X. And then last is the couple. We don't care about these, so we'll just add that on as a positive 100. Yep, exactly. So no Newton's second law. Moment equation says negative 3.47 plus 100 plus 0.3535 F12Y minus 0.3535 F12X is equal to the mass moment of inertia, 0.16 repeating, times alpha for body 1. And I'll save that as equation 1. So we have negative 0.3535 F12X plus 0.3535 F12Y minus 0.16 repeating alpha 1 is equal to negative 96.5
5.3. So far we have one equation, 3 variables. Even though our free body diagram had this RA in it, it didn't appear in our moment equation, so we don't have to worry about that. Any questions about the first body? So now body 2. Does this one have a fixed point? Nope. So the about point is going to be the center of mass. The mass moment of inertia about the center of mass is just 1/12 times the mass times the length squared. What do you get for that? Wait. Oh, okay. 0.0416 repeating. Kilogram meter squared. And then free body diagram. We have the weight at the center. At the joint, we have the force on 2 by 1, which is negative F12. And then for this one, we have a clockwise couple of 100 Newton meters. I'll draw that as counterclockwise and just call it negative 100. The row force moment. Our about point is the center of mass. So I'll start with the weight. Row vector is 0. The force vector is 0, negative 19.62. And the moment is 0. Then we have that force 2, 1. The row vector is positive 0.1768, negative 0.1768. The force vector is negative F12x, negative F12y. And the cross product is negative F12, nope, negative 0.1768 F12y minus 0.1768 F12x. And then the last thing is the couple. We don't care about this stuff, and it just gives us negative 100. This time we have to use Newton's second law because there's no fixed point. So 0, negative 19.62. Plus negative f12x, negative f12y is equal to the mass moment of inertia, 0.0416 repeating. Nope. I know. Okay, yes. Yeah, that's true. Scott would have been gone so long ago. And then, okay, and what's the acceleration that we're dealing with? The acceleration of the center of mass. Last time I did a problem, I wrote that out as acceleration of the center of mass of 2. The only accelerations we ever have in these problems are center of masses, so centers of mass, so I'm gonna just write this as A2, but that is the acceleration of the center of mass, and X and Y. And so we have equation double star that says negative f12x minus 2a2x is equal to 0. And equation 3 star that says negative f12y minus 2a2y is equal to positive 19.62. And then step 5 is the moment equation. And that says negative 0.1768 f12x minus 0.1768 f12y minus 100 is equal to the mass moment of inertia times alpha 2. So that gives equation 4 star that says negative 0.1768 f12x minus 0.1768 f12y minus 0.0416 repeating times alpha 2 is equal to positive 100. All right, so now we have 4 equations. You always get one equation from the body that has a fixed point, 3 equations from bodies that don't have fixed points. So we have 4 equations. Look at this problem, the original problem, and tell me how many variables we have without, like, you can figure it out without even thinking about it, if you think about it the right way. Anybody have an idea?
How do I not think about it and think about it at the same time?
So don't think about the specific variables. You just know, how many variables you're going to have if you think about how many constraint equations are going to come from the points. We never use constraint equations at the fixed point. 6. We never have any there. Here, what kind of constraint equation are we going to have? What's that constraint equation going to say? It's going to say the acceleration at B according to member 1 matches the acceleration of B according to member 2. So that's 2 components of, that gives us 2 equations. And so we know that after doing Newton's laws, we need to have two more variables than equations. Okay. So let's think about what those variables are. Well, we have F12. We have acceleration of the center of mass of 2. Yeah, well, we're assuming that the ball is just sort of part of that member. You know what I mean? They're all connected right now. Alpha 1 and alpha 2. 2, 4, 5, 6. So we have 4 equations, 6 variables. That means we need 2 constraint equations. And that's going to come from saying the acceleration at B, according to member 1, I don't really have a good notation for this, is equal to the acceleration at B, according to member 2. So we'll start by calculating the acceleration at B according to member 1. So the acceleration at B, anytime you have a fixed point, every point is just in circular motion around the fixed point. So we're just going to use the watermelon equation. So this is equal to alpha 1 cross that r vector is the vector going to B from A plus omega 1 cross quantity omega 1 cross quantity B minus A. So that's 0, 0, alpha 1 crossed with, what's the vector going from A to B? Yeah, right. So I think it's 0.3535, 0.3535, 0. And then plus both of the bodies have angular velocities of 0, 0, negative 10. And again, the r vector is 0.3535, 0.3535. Okay, could a couple people calculate that?
External force applied to the elbow.
I don't know.
Don't know.
I don't think so.
Like if that's the force at the inside, the very inside.
Mm-hmm.
So wouldn't that be just the amount of force that is happening all at the same time?
That is the force that the forearm applies to the whatever humerus, I guess this is.
Okay. And so
that's the force that the cartilage inside your elbow is having to deal with at that instant of the throw, which is related to injuries.